Hello everyone, and welcome to the weekly Vega Fairground or Testnet Jam. My name is Dagan. I'm a community manager at Vega, who you might have seen here and there and active on the Discord server. This is an ongoing series that takes place every Thursday at 6 p.m. UTC plus one or British Summer Time, where each week we take a deep dive into an aspect of the Vega protocol with a member of the Vega team or a special guest. Then we usually follow with an open Zoom room so that any keen attendees may have a chat with the team and or follow up on some of the themes covered in the presentation or discussion from the call. This week we're really lucky and we have protocol founder Barney, who you might recognize from various podcasts or presentations about what makes Vega and the problems that we're trying to solve. Today, Barney will be talking to us about the architecture behind Vega and the decisions that have been made along the course of the protocol's lifetime. As always, some housekeeping before we begin. Whilst Barney is presenting, you are free to ask questions in the Zoom chat, in the Twitch chat, and he will answer those at the end of the call. About 5 minutes before we end the session, I will post a Zoom link in the Twitch chat, and then we encourage you to come along and ask any questions and continue the discussion with us. And we're always happy to have anyone that decides to join us. So without further ado, I will hand over to Barney, and then I'll be moderating from behind the scenes in the Twitch chat. Over to you, Barney. Thank you.
Thanks, Dagan. Hi, everyone. I'm Barney, and as Dagan said, I'm one of the founders of the Vega project and sort of key designers of the protocol. I'm here today really to talk to you about the architecture of Vega. We're going to talk about a few different things in this. We're going to cover a few different sort of levels of abstraction and ways of thinking about this, with the aim of giving you a bit of an understanding as to how Vega works. So I'm just sharing my screen now, and you'll see the slide from node to network and beyond, the architecture of Vega. So that sort of gives you a flavor of what we want to talk about. We will sort of start off actually perhaps at the beyond, looking at the sort of high level. We'll actually start off with giving a context a little bit on what is Vega for anyone who needs a recap or some context there. Then we'll take the sort of 50,000 foot view and look at what Vega looks like from the outside and from the world of blockchains and computers in general. Then we'll zoom in on the Vega network itself and talk about the types of nodes and the architecture of the validator and API nodes. And then we will finish off by talking a bit about the Vega collateral bridges, which are the way that Vega talks to the rest of the blockchain ecosystem and the way that sort of money or value makes its way onto the Vega network. So, that's what we want to cover. Hopefully this will give you an insight into some of the decisions we made, some of the reasons we made those decisions, some of the advantages that gives us, and some of the things that you will see in the wild when interacting with testnet and in future with the Vega mainnet. So moving on, what is Vega? Vega is a decentralized proof of stake network, and it's optimized for trading. So let's talk a little bit about what that means. What that means is that whereas networks like Bitcoin are really designed to move Bitcoin around. Effectively, Bitcoin is designed to create censorship-resistant, decentralized, permissionless money, and it does that with proof of work, and it does that very effectively and in a very secure way. But it's really not capable of doing a huge amount else without side chains and other chains. Ethereum is a slightly different network. Again, Ethereum is designed to be a general purpose blockchain. It can run sort of bytecode on the EVM. It can run smart contracts, and it has lots and lots of advantages there. It's incredibly flexible. It can do lots of things, but it's also relatively slow, relatively expensive. And actually, when you look at things like trading and other high performance applications, the Ethereum network is not well optimized for those kind of use cases. Other networks out there are optimized for different use cases. IPFS and Filecoin are optimized for the use case of storing and retrieving and accessing data and creating a decentralized kind of internet and data store. And they've made different choices again. And this is important because at Vega we've made specific choices in order to optimize for trading, particularly trading derivatives and other more complex products. But Vega is also very well suited to spot trading as well. So what that means is that the Vega network and the Vega nodes, rather than running sort of a bytecode VM that can allow you to code anything, actually run a kind of workflow, a trading workflow that looks a little bit like what you might find in an investment bank or in an exchange. That means it's optimized for trading. It means that it understands concepts like settlement, concepts like value, risk, margin, transfers. They're all first class primitives in the Vega system, which makes them perform highly well. It means that the Vega network is sort of batteries included. So rather than having to code up your own pricing algorithm or code up a risk algorithm, you have a lot of sort of features provided for creating markets and trading and products, which means that the users can get on with the job of creating those markets, specifying them well, providing liquidity and all the other tasks that are involved in trading. That does mean that the way we've architected the network has a few fairly special considerations. So firstly, we are very interested in performance, particularly latency. So we believe that latency is very important for trading. I've spent a large amount of my career working on various types of trading systems and platforms and matching engines, and I've seen firsthand the value that is sort of derived from having low latency trading and having sort of quick access to prices and to understand the impact of orders and market changes. So Vega values latency being low. Vega also values the ability to have throughput, and that's both sort of throughput on a node, but also having a simple enough architecture that it's easy to shard Vega out to allow different markets to effectively run on different subnetworks in future, which will allow massive horizontal scaling. And Vega is also interested in the cost of trading. So it's interested in having reasonable fees. It's interested in making it easy and cheap to place orders. In fact, on Vega, it's free to place orders and charging based on the the trading fees based on the amount that's being traded. So to take a look at the 50,000-foot view of what this starts to look like, you're going to have to excuse my incredibly lacking in artistic skills. I've been scribbling these on a tablet because it's just a sort of quick way to get these things down, but hopefully they will give you a good sort of feeling for what's going on. So this is a very high level view where we've kind of zoomed out and we're looking at the Vega network from above, and we're seeing that there's actually multiple levels of connectivity between Vega and Ethereum, and in fact not drawn here, but in future there will be connections between Vega and other blockchains. So blockchains like Polkadot, for instance, might be connected to Vega, but even Bitcoin will be connected. And Vega is actually architected and designed to allow for many of these types of bridges to happen. One thing that's worth mentioning is that actually another of the design decisions we took when creating Vega was we looked at the world of crypto, we looked at the world of ERC20 tokens and Bitcoin, and we said, we actually don't want to create a competing standard to ERC20 or a competing cryptocurrency to Bitcoin. What we're interested in doing is creating a way to trade those things that people are already creating much more efficiently and effectively, and to have a much wider range of financial products that exist on a completely decentralized network. So Vega is actually designed not to have any native tokens at all, and always to use bridges, even down to the fact that the Vega token itself is an ERC20 on Ethereum, and staking with the Vega network happens across the bridge. And when we come to talk about that, we'll see that has some performance advantages and some security advantages, in addition to being a way that Vega interacts well with the sort of existing crypto ecosystem. So at this level, what you can see is that there are those connections between the Vega validators, the kind of yellow squares or the yellow diamonds, and the Ethereum validator nodes on the Ethereum network. That's the data flowing across the Vega to Ethereum bridge. The validators on the Vega network, there's a relatively small number of them. There are going to be far fewer validators on Vega than on Ethereum, partly because Vega is a proof of stake network, and partly because of the trade-offs between sort of performance and security that makes sense perhaps for trading and sort of more ephemeral sort of trading transactions rather than the Ethereum blockchain. And we'll get onto some of that as well. And then you can see the little circles outside, and this is an important part of the architecture of Vega. Although there's a small number of validator nodes, there'll be many read nodes, and those read nodes can do a few things. Firstly, they receive all the transactions from the network in the same way the validators do, and they verify those transactions. They check that the blocks and the transactions all make sense. They check the signatures and the headers. So they actually verify the data. They verify that the data has passed consensus. The validators have voted. They process those blocks in the same way that a validator does, but they just don't participate in the consensus part of the algorithm. And then what they do is they actually store they aggregate, they store, they process the data and the events coming out of the Vega protocol, and they serve that data up as a set of rich APIs. Again, that's very important. The kind of APIs that that you want to see when you're doing trading are things like, give me the hourly prices every hour for the last year. And that's not something that you can easily or quickly do on an Ethereum node without additional processing, but actually the Vega API node software allows for those kind of queries, and it actually supports gRPC for high performance queries, REST for kind of simple, easy to script queries, and GraphQL for sort of interactive front end queries and mutations. So those API nodes perform a hugely important function, which means that each API node effectively serves up an API to the users of the Vega network that looks very similar to what you might see if you were actually interacting with a centralized exchange. And if any of you have ever taken a look at the Vega APIs, you'll see what I mean in terms of the fact that the operations that you have are very similar to exchange operations. You can see account balances, you can see prices, you can see trades, you can see position information. So that's the high-level architecture of the network. Vega is designed very much so that the many bridges can be created in future, and it's also worth saying that this is a completely decentralized network. These validators are running a proof-of-stake network. The Vega project team have no control over this network. The token holders control the network through governance, and the validators control the network through running the code. And so Vega is a truly decentralized network like Ethereum. And given the performance of Vega, it's probably the first network that I'm aware of which provides these kind of products. So starting with, for instance, cash settled futures with a performance that's similar to a centralized exchange, and with a user experience that's like using something like BitMEX or Binance, but actually on a completely decentralized and censorship resistant network. So that's the high level. And what I'm going to do now is zoom in a little bit to the yellow squares on the Vega network itself. And when you look at the yellow squares on the Vega network, you can see that the Vega node is doing a whole bunch of stuff. So first off is the most obvious part, and that is this sort of the consensus. Let me see if I can get some annotation here. So this is happening here, consensus, where Vega is talking to the other nodes. So that's where each validator node is connected into the network of other nodes on the Vega network. They're gossiping transactions. They're talking to each other about what transactions are there. They're voting on transactions, and eventually they're coming up with a list of transactions in each block in the order those transactions occur, which every validator agrees is the next block, and those are the transactions to be processed. Transactions can basically be of one of roughly three types. There are sort of, this is a slightly vague classification, but roughly three types. The first one is trading instructions. So that is things which you're doing that relate to trading. That could be placing an order, it could be canceling an order, but it could also be committing liquidity to a market or changing a liquidity commitment or other aspects of market interaction. Governance, proposals, and voting. So when you're interacting with a node, you're submitting governance proposals sometimes, which may want to change a parameter, may want to change a fee rate, may want to change some other risk parameter, and you'll also be voting on those governance proposals. So that's another type of transaction. And then bridge events. So this is where Vega is bridged with other blockchains, and so events are coming in that have been observed on those blockchains and that effectively are being brought through consensus. So when we'll see this when we talk about the bridge more, but when an event is seen, say on Ethereum, that for instance might be a deposit or a successful withdrawal, that event is effectively verified by every node, every validator, and if every validator agrees that that event did happen as it's been seen, then it goes through the consensus layer and it creates a transaction into the Vega system, which acknowledges on the Vega chain that that event happened on Ethereum, and that's a part of how the bridge architecture works. Obviously, this all happens with the other nodes participating in consensus. So at this point, what we have is we have an ordered list of transactions, and so this is just a set of data saying what needs to be processed. At the moment, that hasn't done anything yet. We haven't generated any trades, we haven't got any prices, we haven't got any positions, we haven't managed any margin. So those transactions are handed to the Vega core, which is the core implementation of the protocol that actually handles the transactions. At the top of everything, you have governance. And the reason governance is the top of everything is because nothing really exists without governance. So every time you trade on a market, that's a market that was created by a governance proposal. So every market, every trade, every position, every transfer can be tracked back to a governance proposal that created the market data structure, that created the order book that you're trading on, that created the asset, that brought the asset that you're trading into the system. So that's why governance kind of sits across everything. Governance then effectively creates the data structures, the markets and the assets particularly, which are used by the rest of the system. And the three key parts of the system to talk about here are the execution engine. So this is the handling of trading instructions. We take an instruction and we execute that against the order book. That means adding orders to the book, creating trades if necessary, updating prices, updating mark to market, and we'll talk to that with the risk engine, and sort of sending that information downstream. So the execution engine handles those things, implements a fully order book based exchange model, and also in future it will have other forms of execution such as RFQ and AMM, or sort of automated liquidity provision. Then we have the risk engine. The risk engine's job is to take the output of the execution engine, which is the list of trades and updates to positions that occur, and manage that risk. It manages that risk by identifying for each participant how much margin they should be supplying. So if you open a position of size 10 on something that costs $100, 100 die, let's say, then maybe that's a position worth 1,000 die, maybe the margin is 50 die. At that point, the risk engine ensures that you have enough margin to cover your position, and if you don't, it closes you out. And it's very important that Vega has some sophisticated risk algorithms that actually understand the probabilities involved and the way to value various different types of products, and that those risk algorithms are used to provide sort of low margin or high leverage compared to other sort of fully decentralized solutions. The collateral engine is another part of the sort of internal architecture of Vega, in that the collateral engine manages all your balances, and this is probably the most similar to something like Ethereum, sort of the ERC20s, where you have many different contracts, each of which one has a balance for every key. Similar sort of thing in Vega. Everyone has a public key. Your public key can have a number of balances. You have what we call a general account in each asset. So you could have a general account in DAI, you could have a general account in Vega tokens, or in wrapped Bitcoin, or in ETH. And in that general account is a balance that's available to you to spend. You also have a staking account, which is your sort of governance balance of Vega tokens that you're using for delegation or you're using for governance proposals. And you also have other accounts per market. So for instance, you can have an account for a margin on a particular market. And that means that when you take out a position, some of your funds are transferred from your general account to the margin account for that market. That margin is maintained in that account, and it's therefore not available to trade with while you've got that position open. And the collateral engine tracks every one of these accounts and their balances. It tracks transfers between them, and it makes sure no funds can ever be sort of gained from nowhere or lost. So the collateral engine has an incredibly important role in ensuring that what happens on the Vega network is sort of happening robustly and that no money is lost. The outcome of all of this, transactions going through the execution engine, through the risk engine, through the collateral engine, is that lots and lots of data is created. There's an internal state of the core, which is the state of the order books, the state of your balances, the state of your open positions and trades. That state is maintained in order to keep all these things running and to do things. But a lot of the data that's created is actually kind of discarded. So for instance, the fact that you just did a trade of size 10 is not much interest to the core, actually. The core is interested in knowing your total position. So if you had a position of 5 and you buy another 5, then your position will be 15. The core will restore that that's 15. But your position of 15 could be the result of 100,000 trades that you've done. And the core doesn't need to store that information. So sort of for performance reasons and to ensure that the core works really well and doesn't take up too much memory, the core will discard that trade information. It'll just keep hold of the information it needs, which is your position amount, your margin balances, your other balances, the order book state. When those things do happen, though, what happens is these events are emitted. Events are absolutely key, and they literally describe everything that's gone on, every decision that's been made, every calculation, effectively, everything that impacts all of the state of the core. And those events will include all of your trades, all of the mark-to-market position changes every time the price changes, all of your valuation, all of the movements, all of the closeouts, everything that happens. And those events can be consumed by other nodes. In the state of validators, what actually happens really is that those events are by and large ignored, because validators are not really designed to be connected to by other people. Validators are designed to sit in a very protected space, connecting to each other, gossiping consensus and processing the core transactions as fast as they can, and really not to interact too much with the rest of the world. They're not really that interested in the rest of the world. They're just very interested in making sure they can produce blocks, process transactions, and validate those transactions. That moves us on to the second hugely important part of the Vega network, which is, how do I move to the next page? I have to stop annotating. Which is, that's interesting, which is API nodes. My annotations have stayed, so let's clear. So the API nodes actually look a lot like a validator node. So you'll see that the top half of an API node is exactly the same as what we looked at just for the validator node, and that's absolutely intentional. It's actually the same code. What happens is that these other nodes are often validators under the rest of the network, and the other nodes form consensus. And you'll see this is only a one-way arrow in this case, because the other nodes form consensus. Your API read nodes gossip transactions and listen to the consensus, but they don't actually participate in the consensus themselves. They take that information from the validator nodes. They still get a list of transactions, though. They still verify the signatures on those transactions. They still verify that the consensus has happened properly. They still do all the cool cryptography that they need to do to make sure that the data they're reading is valid and secure, but they're not participating in consensus itself. They still process the data through the Vega core, and they still gain all the state, and they create the trades and everything. But what the API nodes are really interested in is these events. API nodes are focused on processing these events and data they get out of the APIs available from the core of Vega, and turning it into data that's useful for downstream users. And so for an API node, what the key processing is ingesting these events into stores. And the stores are basically databases. At the moment, they're all implemented using Badger, which is a key value store, embedded key value store in the built into the sort of Go API node. But in future, there will probably be a number of different types of store for different purposes. The events sometimes need aggregating or processing. So for instance, if you want to be able to see hourly prices, then you need to aggregate all of the second by second trade data and create some way of indexing into it and getting aggregated hourly prices, hourly volume, and other data. Sometimes the data can just be stored. Sometimes you have multiple versions. So as an order trades, it might be submitted and it might trade and go through, having 500 volume available down to 400, down to 350, down to 200. And each of those versions can be stored and be made available. The API node then serves up a set of APIs, and that's available with gRPC, REST, and GraphQL endpoints. And those APIs are used by the users downstream here, who can connect into the API node. Without the API node, if you were just connecting to the blockchain, you would have to listen to this whole stream of events, process the whole chain yourself, build databases, process the data, and interact yourself. So the API nodes have an incredibly important role to play. They also allow you to easily submit transactions via the APIs. They allow you to submit transactions back into the consensus of the blockchain. So you effectively connect into a node, submit a transaction into consensus, and have that become, and if you've signed that transaction and it's valid, have it become part of the network, which is how you interact with the network. So these API nodes perform a really important role, and actually a huge amount of work is going on and will continue going on over the coming months to provide very rich APIs for users of the Vega network. So that's kind of looking at the internals of the Vega network in terms of the nodes, and we've got the validator nodes performing the role of actually running the network, keeping it secure and deciding what trading happens, and the API nodes performing the role of processing all the data that comes out of that, serving it and making it available to users. Then the last one, and by far my most embarrassingly bad picture, is the Vega collateral bridges. These are a really important part of the network, and although the picture I've drawn doesn't make it look like very much, it's really important, and the sort of the cryptography, the security, and the design of this is key to making sure Vega works very well. So what we effectively have is on the right-hand side, we have the Ethereum network and some key smart contracts. And on the left-hand side, we have the Vega network and some validators floating around there looking like little sort of squares. The bridge happens in two directions. And so the first thing I'm going to talk about is the architecture of how Vega validators can control something going on the Ethereum network. And this happens through what's called the multi-sig control contract. And the multi-sig control contract is a very clever little contract that effectively knows the public key of every single one of the validators. So every validator's public key is stored in multi-sig control. And every single time a new validator is added, multi-sig control is updated. And every time a validator is removed, multi-sig control is updated. So that's the one thing that multi-sig control can do there, for example. The way that it works is if you want to do something that's controlled by multi-sig control, what you need to do is you need to get a majority of validators on the Vega network to sign it. So multi-sig control is not interested in your Ethereum key. Multi-sig control is interested in the private keys of these guys. And if these validators all sign your transaction, they sign a bundle with the transaction in, the signature of the transaction, and they submit that to multi-sig control. In fact, anyone can submit that to multi-sig control. Once that's submitted to multi-sig control will validate that signature and say, yes, a majority of Vega validators did want this to happen, so I'll let it happen. And so that's a way that we can allow the Vega network to express control over the Ethereum network, because multi-sig control allows any Ethereum smart contract to be controlled by the Vega validators. We use that to control multi-sig control itself with the update function. So every time a new validator is added or removed, we're going to update the multi-sig control list of validators. And we're going to do that by having the Vega validators sign the additional removal of the new validator. Equally, we're going to do that whenever there's a withdrawal. So if you've got some money deposited with the ERC20 bridge and you want to withdraw it, withdrawing it requires permission from the Vega network, because maybe you deposited it and maybe you then lost all that money. Maybe that money is now been lost to someone else and you actually have a zero balance. So when you want to make a withdrawal, you make a request on the Vega side, the validators check that it's okay. The validators then sign the bundle for the withdrawal, which you can then submit. A multi-sig control will check that bundle is okay. And if it's okay, it'll allow the withdrawal to happen on the ERC20 bridge and you can get your money out. Equally, when you deposit money, it happens the other way around. So if I'm depositing money to the Vega network, then instead of using multi-sig control, I can deposit straight into the Ethereum bridge contract. That's the Vega contract address. That contract will then emit a deposit event. And then the Vega validators are watching the Ethereum blockchain as well. They see this deposit event and they notice that the money is deposited. They wait for enough confirmations and then they credit your account on Vega. A similar thing actually happens with the withdrawal. Once the withdrawal has been processed, it's necessary for the successful processing of the withdrawal by the bridge contract raises an event similarly, which is watched by the validators to update the final status of your withdrawal. So that's how that happens. And what that means is that when you place money into the Ethereum ERC20 bridge contract as a deposit, you're putting that money, you're putting those funds, those ERC20 tokens, in control of the Vega validators. The Vega validators are now the only people who can decide what happens to those funds, and an individual validator can't steal them. Like one validator here can't steal them, or two validators. You need a majority. You need 2/3 plus one of the validators to say, yes, these funds should be sent here, and then they'll be sent. So by doing this, you place your funds in the control of the Vega network, which allows the Vega network to credit you with those funds and allow you to trade with them. There's one final contract to talk about, and that's the staking bridge. So obviously Vega is a proof of stake network, and Vega uses its own Vega token, which is an ERC20, for both governance proposals and decisions and for proof of stake. When it uses it for governance decisions and for proof of stake, we actually use a different bridge contract. And the interesting thing about this project contract is it doesn't use multi-sig control, and it doesn't give the Vega validators any control whatsoever. So the bridge contract actually only processes events in the same way as the sort of deposits. the stake and the unstake events. So effectively, stake added and stake removed. When you stake some tokens on the network and want to use them, you stake them to your Vega key. The network can see that event, and it credits your Vega key with that much voting power and that power. When you unstake, you do that unstaking on Ethereum as well. So you both stake and unstake on the Ethereum side. And when you unstake, the same happens in reverse. The unstake event is raised, and the validators in the Vega network remove that much voting power from your credit and remove any delegation that's associated with it. Why do we do this? Because we could have simply designed this to use the ERC20 bridge. We could have just said, yeah, let's just use the ERC20 bridge to deposit with the Vega network. That's okay, and that would actually have worked, but we noticed the opportunity to add more security to the system. And what I mean by that is, if someone's able to take to influence the validators in a bad way and cause something bad to happen, potentially they can take control of some stake via the ERC20 bridge. Now, it's hopefully reasonably unlikely, and hopefully the network will be secure. But something we do know is that the Ethereum network has been running for a very long time and has demonstrated a very high level of security. It's very expensive to cause a 51% attack on Ethereum, and the results of what's gone on have gone through a lot of validators, and it's a real big issue and a very difficult problem to corrupt the Ethereum network. So we noticed the opportunity to import some of that security into Vega. So effectively, even once you've staked your tokens and you're using them to delegate to a validator, even if someone gains control of every single validator on the Vega network, they still can't steal your staked Vega tokens. That means that your staked Vega tokens still belong to you, and so do everyone else's. So even once they've taken control of the validators, perhaps by inserting some malicious code somewhere, perhaps by bribing people offline, the token holders can look at it, sit back and say, we're going to go find some new validators that we trust, and we're going to stake to them instead, and we're going to restart the network over here from a certain point in the chain, and the people who took over the validators have achieved nothing of lasting value. They haven't taken over the network. And so that gives us an additional sort of layer and level of security that we wouldn't have been able to get if we had used the ERC20 bridge. And it's something that's we're very, very proud of and happy about. We think it's a really nice sort of security feature, especially when launching a new network, to have this sort of built in some of the security from the Ethereum network. So that's a look at the staking bridge. And the key thing is we kind of have a design here for this this interface between the Ethereum and the Vega layer, and it's generalizable to many types of blockchain. It's effectively an event queue system, which is looking at these events, and it's the multi-sig recovery process that goes on in multi-sig control. This can be implemented on pretty much any blockchain that supports smart contracts, and so we actually expect to sort of standardize this interface further, document it, and see a number of additional bridges be built, and potentially even integrations between Vega's bridging solution and to work with formats and protocols like IBC and other inter-blockchain kind of formats, so that we can actually bridge to more chains even more quickly. So that's a quick look at the collateral bridges, and that's the final part really of this. We've been through the collateral bridging to other chains. We've been through the API nodes and the important role they play in enabling people to actually use the Vega network, and enabling things like Vega's rich console trading interface to be built. We've been through the Vega validator nodes and the architecture of how they process events and how they work. And we've also looked at this sort of high level sort of architecture of the whole system. So that's everything from me for this portion. I assume that we will now have the Twitch video, not Twitch video, the Zoom video chat link will have been shared. And we can move on to the second portion of this. Thank you, everyone.
Thank you, Barney. That was really insightful. Also quite fascinating to hear about the imported security from the Ethereum network. I hadn't thought of it that way before. I have a question. I have some questions for you. Okay. Because we're talking about architecture here, what do you think is the most significant architectural difference in Vega protocol compared to other decentralized derivative protocols in the industry?
It's a good question, because the most significant, I guess the most significant architectural difference actually is that Vega protocol is a network. So the vast majority of other DeFi protocols that you look at are not networks. They are probably built on Ethereum, although there are people building them on Polkadot and other places. So they are a protocol built on top of another network. That means that there's a layer of network where the network tells you what you can and can't do. That network kind of tells you a lot of the security and performance implications and costs. The network tells you how fees are set, how much gas costs and everything. And what you're doing is you're writing some code on top of that network as a platform to try and implement derivatives. Vega is very different because Vega is a network that's actually designed and optimized for trading. And so the architecture, for instance, of how we do fees is is linked directly to the design of how we do how we actually implement trading and implement the Vega system. But it also means that when we're designing Vega as a protocol, there's a lot longer lead time on certain things. Forking Uniswap or creating, a new AMM-based protocol involves doing a relatively small number of things. You get a lot of stuff from Ethereum in terms of validators and security. Launching Vega means not only designing the protocol, but getting the validators stuff working, making sure there's security, making sure that the network will work, and being able to launch a network. So there are downsides, which in terms of the amount of work to do and the security and the complexity, there are upsides in terms of the ability to optimize every aspect of the network and the architecture for the specific use case.
Yeah, thank you. That's very comprehensive. I like how you spoke about it on the Delphi Digital podcast, where you said we're just trying to build the most efficient way of possibly doing derivatives, and that best way would be to do it on our own chain that bridges to other chains, and so that we can have the best trading experience for the users.
Yeah, absolutely, and it's probably worth us touching on that a little bit. Actually, the goal of Vega is to be able to replace centralized finance with Vega. Is to be able to say you would go to your commercial banker, you go to a bank, or go to use Robinhood to do this thing, but actually instead of paying them, you can use a decentralized peer-to-peer solution, which is sort of run by its users, which is fairer and which is faster to innovate. So Vega wants to be able to replace those centralized platforms. And something you see if you look at centralized finance is the platforms are incredibly heavily optimized. They're mostly written in C and C++ a lot of the time, or maybe Rust if they're newer, Java sometimes, but they're written in high performance languages. They are no holds barred, incredibly performant and robust systems that have been built over years to handle huge volume. And without taking Vega and taking the industry of the crypto industry and the space to that fight, we don't stand a chance. And so it's really important to us that we're designing something that not only is a good stab at being one of the more efficient and one of the best solutions now, but actually, because we control as a project and as a community, we control the whole network and the design of Vega, and we can optimize it for trading. We can continue to iterate and squeeze the performance out of it in a way that protocols built on other networks can't.
Yeah, 100%. And it'll be very fascinating to see how it evolves over the coming months as we build out those feature sets. But yeah, that's all from this week. You have a lot of thank yous in the chat. They like all your lovely drawings as well. So Vega Fairground Jam is a weekly thing. We have the same format next Thursday at 6 p.m. British Summer Time. Do attend. And for the time, for now, we're going to go and head over into a separate Zoom room where if you have any further questions or you'd just like to chat with Barney or any of the team members, you can hang out with us for the next 15 or so minutes. So we'll see you there. Thank you. And this will be uploaded on YouTube in the next few days as well. So bye-bye. Until next time. Thank you, Barney.